being recorded.
I'm really happy to hear and see all of you here. My speech is called Noble Metals in Basaltic Magmas Worldwide, a study of modern and prehistoric lavas in the Tolbachik of the Tolbachik volcano, Kamchatka. So the first question is, we have heard here a lot of beautiful talks about deposits and other stuff like this. Why do we need to study volcanic rocks which are apparently barren? And first answer I think was given by the first our keynote speaker today, that it's interesting to understand the sources of various melt in various regions of the earth. The second is, to my opinion, is that sometimes we need to find some small bricks to understand the things we don't know about magmatic process. Here you can see 3 pictures of ores from Ural-Alaskan type complexes. These are complexes which you can find in island arc environments above the subduction zones. And so you can see that here we can speak about 7 times orders of magnitude concentration of platinum during the magmatic process. I would remind you that if you're speaking about silicate sulfide partitioning, we have only 6 orders of magnitude, and this is the most extreme evaluations. So, to my opinion, I'm not going to tell you about the theories of how this platinum can form. So it's just platinum nuggets without apparent role of sulfide. So how do PG behave when the sulfide has a day out, I would say. So I'm not telling you that I will answer a question here, but this is the point, just to find some small bricks from which we will be able to build future models. And volcanic rocks has advantages. They're young, they are untouched by metamorphic processes, secondary processes. So everything is still very hard when I'm speaking of them, very complicated, but easier when comparing with the intrusive rocks. Tolbachik volcanic massif is located in Kuril-Kamchatka arc, which is one of the most active volcanic arcs worldwide. Volcano is active for at least 10,000 years. Here we will discuss the samples of lavas that erupted in, say, last 2,000 years approximately. Last eruption was in 2012, 2015. So here are some references, brilliant works where everything is described in the best way it's possible. So just a picture of the volcano. Tolbachik is an extinct volcano. It was erupted thousands of years ago. Tolbachik is active. During the 20th century, several times it was able to find the lava lakes, but the most active is this field of monogenic cones. So one second, laser point. Yeah, these are cones. Most of them monogenic, so they were formed during a single eruption event, and most of the samples I'll discuss here are from them. Before we go into PG, petrochemistry of Tolbachik massive rocks. So which types of rocks we have? Here you can see blue field is Kamchatka rocks, all volcanic Kamchatka rocks from GeoRock database. Orange points similar from GeoRock database, but only Tolbachik, and colorful, large, beautiful points apparently are our analyses. So the same points that were analyzed for PG. So first of all, we can see that rocks are bimodal. You clearly can see that there is a majority of rocks are low magnesium. So say 3 to 5% of magnesium oxide. And the second group, also big but less dense, is high magnesium rocks. There's a clear gap between them. Of course, some points exist, but the gap is evident. So the second thing which we can see here is that there are 2 series, high potassium and mid potassium. We are going to speak only of high potassium series. Modern rocks are generally of this high potassium series. And this is important because we're speaking, it is unitedly accepted that high potassium series or rocks have the same origin, the same mantle source, and the difference between the high magnesium and low magnesium rocks, high magnesium, low magnesium, is that they underwent differentiation in some intermediate camera below the volcano. So we will be speaking only in terms of comparing these 2 types of rocks. Speaking of the terms, I will refer them as high magnesium basalts and low magnesium basalts, but you can see there are pretty high amounts of potassium and sodium. So the correct names are trihigh basalts and basaltic trohandizites, but just in case. PG and gold content in Tolbachik lavas. So PG and gold contents are apparently low. Apparently PG are the lowest. Here they are plotted with analytical uncertainties, and what is apparent that unfortunately we are not going to use ruthenium in our comparison because the analytical mistake is too large, but we can use all other elements. Also, the second thing is that we can see clear incompatible behavior of iridium and rhodium, so they accumulate in more magnesium, more olivine and chromium spinel rich magnesium basals, and their content dramatically decrease, especially if we're speaking about of iridium, to more evolved members of the series. However, the same is observed about platinum, can be said about platinum, but it's just not visible in this diagram because of several anomalous samples with extremely high content, which ruin the scale. But actually, to much less extent, platinum always also behaves compatibly. And palladium and gold content is not related to magnesium or magnesium oxide content, or even shows negative correlation. So they behave incompatibly. And also, there are anomalous samples when we're speaking of gold. So we have seen these anomalous samples, and I need to say a few words about them. There's Nugget Effect and issue of homogeneity of PGE distribution. So apparently, I think all of us know what is Nugget Effect. This is randomly some small particle may be or not be analyzed in a certain amount of powders used for nickel sulfide fire assay. So we decided to analyze 14 rock samples from the same lava flow in Pond 2004. So 14 samples of high magnesium basals, and we see that for many elements like palladium, platinum, they are pretty homogeneous. There is big scatter when speaking of iridium, and what is more significant, some anomalous gold-rich samples. I believe that this is a clear result of Nugget Effect. In other levels, there were also some gold and platinum anomalies. So we tested one of them by making a duplicate, and it yielded once again high platinum content. Some platinum anomalies maybe are not due to the Nugget Effect, but just due to the high content of platinum. So I said that platinum and iridium behaves compatibly, so they accumulated in more magnesium oxide rich rocks, more primitive rocks. So this is just a little excursion to the previous published works. I know in chat Steve mentioned this work of Dima Kamenetsky and his colleagues, where they managed to find pretty large inclusions and platinum nuggets in nuggets of platinum always. This is platinum, not iridium, but platinum in spinels, including arc spinels. Also, IPG and rhodium may be concentrated as an admixture in the chromium spinel lattice. So I believe that this explains why in certain conditions these elements may behave compatibly. Palladium is much more interesting. Palladium content is significantly low in low magnesium basals. To make some constraints about the reasons of such palladium behavior, we decided to check if there was an evidence of sulfide saturation by plotting copper versus magnesium oxide and copper versus potassium. So on the second graph, you can see copper plotted versus magnesium oxide, and there is a pretty large scatter. So it may seem like there is no relation, but when you plot copper with potassium against potassium, apparently incompatible mineral, you can see here not ideal, but good and valuable significant correlation. So it is evidence of sulfide saturation, that sulfide saturation was not reached and sulfide was not removed during the process of evolution from high magnesium to low magnesium basals. Or was it? So if anybody knows the previous works on Tolbachik volcano, I would strongly recommend to read this brilliant work by Michael Zelensky and his colleagues, who managed to find sulfide spherical globular inclusions in olivine, which are apparently the result of capturing of sulfide melt. Moreover, you can see when there are some particles of PGE, platinum, palladium, other elements, and also the sulfides comprise PGE in their lattice themselves. So how can be explained? We see mineralogical evidence of sulfide immiscibility, sulfide saturation, and we see the lack of this evidence when we're speaking about geochemistry of our rocks. The explanation is quite simple. If we'll dig deeper into the work of Zelensky, he mentions that only in 0.2 to 0.6% of olivine crystals, of primitive olivine crystal, comprised any sulfide inclusions. So as I explained, sulfide saturation took its place during the evolution of Tolbachik magmas. However, it was limited in time and possibly in space. So some droplets of sulfide melt were captured by olivine crystals and preserved, while the major amount was dissolved, possibly because magmas became more oxidized or some other conditions changed. So we're speaking just about facts. So why does palladium behave so differently from other PG? I believe someone already mentioned this, that PG solubility in silicate melt, we are not speaking of sulfide, we're speaking of silicate melt, correlates positively with oxygen fugacidity temperature of the melt, but you can see that there is a dramatic difference between palladium, gold, and solubility of other PG. When you consider this diagram, of course, this is experimental data. Things might be a little bit different in real system, but you can see that there is interception between the concentration of platinum and palladium in natural existing melts and the solubilities of these elements. So this tells us that these minerals of these elements may precipitate, while for gold and especially for palladium, it is virtually impossible. If you remember on the slide when I was speaking about PG inclusions in chromium spinel, I underlined that palladium wasn't found. Well, the only element that wasn't found in these inclusions is palladium. Apparently, it's because in sulfide-free environments, palladium is still too soluble in silica melt and is not crystallized. So we decided to compare palladium in ARC and more rocks. So palladium content of more basalt drops drastically when during the evolution they reach approximately 9.5 weight percent magneon. This is a recent paper by Howe and his colleagues. What may be that's likely as a result of sulfide liquid fractional crystallization. We decided we cannot calculate the amount of palladium in the initial melt because, of course, it's interesting to understand the concentration of initial melt. But we have primitive melts with up to 11% of magnesium on, and also we have a fact that there is no significant correlation in ARC or rocks, precisely because of the lack of sulfide saturation especially in these ranges. So you may see these colorful circles. There is a drop in palladium content in the most evolved compositions because at some point, even in oxidized ARC rocks, this sulfide saturation is reached. But we decided we can just take this approximately framework. So I didn't picture it here, but I written down here, and we think that the possible range for initial ARC melt concentration of palladium is 3.5 to 11 ppb. So this is indirectly supported by this diagram. This is actually a result of summary of huge amount of data from GeoRock, these two fields for ARC and more rocks of a certain rather primitive composition. So we believe that palladium content in ARC rocks and subductionary rocks is genuinely initially high than if we're speaking about more rocks. We decided to account for all factors which may be responsible for difference in palladium content, and what we found, this is just a brief show because there are much more numerous factors. What we decided is that all scenarios trying to explain the difference in palladium content that involve different conditions, different melting conditions, different residual minerals are broken by the idea that palladium, due to its very high solubility, will be almost immediately transferred to melt. There is no or nothing concept. Oh, I'm sorry, there is a typo in last name. Sorry. So we decided that at this point, our working hypothesis is that high palladium content in ARC rocks may be only a result of higher palladium content in a molten source of metals. So during the refertilization, or maybe just some enrichment in subduction zone. Conclusions: palladium and iridium content is homogeneous for a particular lava flow. Incompatible behavior of both copper and palladium in magmas with the composition range up to 10% magma implies a limited influence of sulfide silicate miscibility. And these sulfide globals, which described by Zelensky, are just obscure and rare survivors of later events. palladium contains the parental melt of Tolbachik close to 6.5 ppb, which is 4 times higher than reported mob dwellers. And we believe that an influx of palladium during refertilization processes of the sebag metal may be responsible for palladium enrichment. So thank you for your attention, and of course, much more information may be found in this paper, open access, if you can download it. And I would like to thank all of my co-authors.